Okay. All right. Hey guys, my name is Sai Kireet Patri. Kind of a tongue twister for some guys, but you can call me Sai. And I've heard Sai also means something in Swedish, but I learned it last night, but I forgot it now. So you can help me with that later. Anyway, so I work in the advanced technology department of Adva. We are an optical networking vendor. And what we do in advanced technology is that we work on research projects for the German government and also for the EU government. And we come up with innovative results and see how and where and what we can do with optical networks to push them to their limits. In this way, we are somehow the tip of the innovation sphere of Adva, so to speak. And today I will be talking about artificial intelligence and machine learning enabled network automation in optical networks. How do we combine three buzzwords together in one sentence? This is my title over here. Anyway, moving forward. So I'm going to quickly talk a bit about what open optical networking is. And the whole idea is that network operators should be allowed to have freedom not only on the layer 2, layer 3 level, but also on the layer 0 or the layer 1 level, which is where we operate, which is the optical networks. So if you want to have an open optical system, you would need to have three things. The first thing being that your devices should be in a partially disaggregated manner, or they should be a partially disaggregated hardware, which means that your terminals should be separate from your open line system, and they should be able to work in different configurations and different settings, and along with different vendors also. The second thing being is that your hardware should be configurable via standardized data protocols. I mean, we vendors, we love having our own data models, and this is what the case has been. But there has been a lot of pushing towards standardizing a lot of data models so that you could buy multiple solutions from multiple vendors, combine them together, and have your network up and running. And the third and the final thing is to have an open commercial model, which means that you need to be able to do network planning with different devices together, put them over there, add some alien wavelengths and whatnot, add some extra pluggables, and have your network up and running and come up with a combined or an open form of RFP, RFQ for your operators. So, and then along with this openness in optical networking, what we want to aim for is to have a unified software-defined networking-based control and management of your whole network architecture. So it's quite a lot of boxes over there, but let's start from the bottom, as we always do in optical networks. We go down to the light level, and this is what we call the open line system right over here. And the open line system is what you have all your optical networking devices, your ROADMs, your filters, your amplifiers, which really builds your network. And then you have the terminal devices where your wavelengths or where your light paths end, where all your client data or your client traffic is aggregated on into the open line system. So here you could have this partially disaggregated pluggables, and you could also have some open source-based pluggables like an open ROADM devices or the open ZR plus pluggables, or something also from some alien wavelengths from some spectrum services, so on and so forth. And your own devices or the vendor-based devices could be managed by an optical domain controller, which is basically going to manage all the services, provision your services on the optical layer. And this should be able to talk to multi-domain controller or a third-party orchestrator, which can then have different services or multi-layer services being provisioned on the top over here, and then everybody knows what to do. Of course, what I'm showing you here is the dream, is what we want to work towards, what we really want to achieve, and I'm pretty sure this, out of my knowledge, I don't think it is really implemented like this anywhere right now. It's mostly in proof of concept stage. But this is what we want to aim for. This is what we want to go towards. And how exactly would we do this whole network automation and how would we use artificial intelligence. This is the whole point of my talk today. So yeah, oh, I forgot that. So you need to have seamless integration in multi-vendor environments. So it's not that you build your whole network with one vendor, try and working with multiple vendors, and this way probably save more money or earn more money as a tier one operator. So let's do a quick introduction about AI ML. I mean, I think a lot of you in the audience here would know better than me, but I'm just going to do it like a very generalized topic description over here. So artificial intelligence, anything could be artificial intelligence. Me pressing this button and then something happening in the background and the slide changing could be this. So any piece of code which can do a simple if-else command 20 years back was artificial intelligence. Today, as and when code grows, as and when software grows, you get more and more complex tasks which can be automated. I think we had Peter who was giving a talk in the previous session about automation. He came up with quite a few good examples of things which can be automated. And there, if you want to mimic something which a human can do, if your code does that, it's already artificial intelligence. A part of that is machine learning. Here you have algorithms which seek data, which learn from data, and once they are trained on data, they create an algorithm which can give you a logic or give you an output based on that particular algorithm. I won't go too much into details here. It's mostly if you have machine learning based algorithms, they have supervised algorithms or like supervised learning or unsupervised learning. But one aspect of it which I would want to talk about is something which is called as deep learning. So here in deep learning, instead of having like a single layer neuron or like a single layer neural network, you try to combine multiple networks and try to move away from supervised learning towards an unsupervised learning. So your the need or the dependence on the data is not as much as for a regular regressor-based algorithm. And the other important part about deep learning is that your decision, whatever decisions or the decision criteria is not pre-decided by the human who is basically coding this ML algorithm. The other part is what we're also looking a lot into is reinforcement learning. Here you create an environment and then you have a state, you do an action, and you get a reward for this action. This is really like a lot of robots use reinforcement learning. And this is, again, a way of teaching your agent or teaching your code how exactly it should behave given a certain input into its own environment. So, quick diagram. I mean, I took it from this website. It's really cool. But machine learning can be split into training and predicting. So what happens in training is that your data goes into this training algorithm, and you get an output of sort of a trained model or a logic. And this trained model can be used for predicting. So if you give another set of data into this trained model, you should give some sort of an output. And this is exactly how machine learning works. All right. And if you look at, so this company called as Gartner, they always publish these hype cycles. I don't know how visible it is right now, but it's usually divided into like you have on the x-axis innovation trigger, peak of inflated expectations. You have a sort of a disillusionment over here. Then you get somehow better, and finally your model becomes productive. And what we are working on, I have just marked a few boxes over here, the different kind of ML algorithms my team is working on, or our team is working on. If you ask me, I myself am not a machine learning guy. I've just learned it from a few blogs here and there, saw some YouTube videos and tried to implement some things on my own. So right now, what I did was try to find whether this is a muffin or a chihuahua, and yeah, I'm at that level right now. There's, or probably try to find if this is fried chicken or a labradoodle. So we are still right. I mean, I'm right here, but our team is spread across all of the hype cycle. All right, so moving on. What exactly do I mean then when I say that we want to use this artificial intelligence and machine learning for network automation and optimization? Two use cases come to mind. The first use case is to try and use or try and take information from your network, from your open line system, from your pluggables, from your transceivers, and take this information and try to analyze it, try to run some, try to make sense of the data first, clean the data, make sense of it, try to run some machine learning models, and then whatever the output, whatever the outcome is, you try to learn from it and try to refine your network back. It could be something as simple as trying to provision your network properly, trying to see if the power of all your channels is equalized. Is there somebody moving the fiber? Is there somebody touching the fiber? Did somebody cut my fiber? So on and so forth. And of course, we can also use it for predictive maintenance. If you keep using streaming telemetry or any kind of telemetry for that matter to get data from your devices, you already know what is the lifetime of the devices. You see that if there is some sort of a degradation, then you can already start ordering newer devices to put into your particular network. So this is one use case. The second use case would be to go on a higher level, like slightly higher on a L, I would say L1 to L3 layer, where you want to work with sort of a multi-layer orchestrator. And again, over here, the dream is to have streaming telemetry like gRPC, GNMI from your devices. And using streaming telemetry, just push it out, check for the insights, use the orchestrator to provision different kind of devices, and finally push your data back into the network using some open APIs, probably working with Netconf or RESTconf, so on and so forth. So the whole point is that we need to turn data into actionable insights and use this data and use these insights to optimize your network and the performance of your network and try and save you some costs. Okay, so how exactly do we get to this? It's not like one day somebody in Adva woke up and said, oh yeah, AI, ML, network automation is a good idea and this is what we're going to do. It's not like that. I mean, we have been working on various kind of ideas for the past few years. And it's sort of like an evolution of an idea where it started. So it started from having, firstly, SDN-based network control. So the moment we had SDN-based network control, we could realize that we can really provision networks without going down to the CLI level of each and every device, configuring each and every device, so on and so forth. And then once we realized we could do this, we also thought that, cool, now instead of having these big configuration scripts to do the provisioning, we can do intent-based operations where we can say that, okay, I want a service of 200 Gbps between Bremen and Munich, and I want to carry so-and-so traffic on this. And if I just put this on my, let's say on my graphical user interface, everything on the background can be handled by a configuration script, which puts things together and configures your entire devices along the path. And this, of course, makes service provisioning easier. And once we were able to achieve this, we thought we have to look at how exactly can we collect data. And so telemetry is one thing, but streaming telemetry is what we want to go for, where it's instead of polling each and every devices, the devices are subscribed already. And this is basically a very scalable way to extract PM data out of your, or performance monitoring data out of your optical devices. So your optical receive power, your signal to noise ratio, so on and so forth. And then you know that whatever data is being carried, which is being carried on your channels, is being carried the right way. And finally, we started looking into some machine learning-driven analytics. The moment we started getting data, you were like, okay, let's do a bit of data science and try and see what we can do. So we could do some time series forecasting, some quality of transmission estimation, just looking at the channels, and try and do some monitoring of different kind of devices together. So this is the whole, let's say, the circle, and you're going to be seeing this graphic a lot in my presentation moving on, but I will explain you why later. So this is a whole cycle, and to build this cycle, or like to come to this cycle, we realized that in our company we need like 3Ds in order to achieve this. So the building blocks are 3Ds. The first D is the choice of devices. So again, at the sake of repeating myself, again, the devices need to have a lot of flexibility in terms of the APIs it provides, how you can provision it, and whether or not it has some form of telemetry over there. The second D is database. So the kind of database you want to take from your, or you want to implement in your whole network, which can really be scalable, which should be easy to deploy and should not take a lot of time to run the queries, and it should be easy to store the data. So your database operations are really important, and this choice really matters. And of course, the third D is data science. Here, you need to have a good knowledge of what kind of machine learning algorithms would work for which specific problems, whether or not this works, or like, let's say, what kind of a problem it is and what exactly is the algorithm you're going to apply. And also, not only that, once you have a big enough team, or once you have some, I don't know, like 5 or 6 ML engineers working together, you also need to create like an internal marketplace where people can store their algorithms, where people can store their data analytics, and which you can share these particular algorithms with each other. And so with these 3Ds, once you have these 3Ds set up, you can try and attempt to do some network automation inside, or use AI ML to do some network automation, sorry. So being true engineers, instead of starting from step 1, we started from step 4. What we did was we first thought that can we already do something with the data which we have. So we had some data from our customers, we had some data from lab tests and some from field trials, and we already had some bunch of data. So we thought, why not just implement some ML algorithms into it, and let's see what happens. So the first, let's say, the research results which I'll be discussing today is from the German government's project called Opticon, where Adva was a part of. And here we came up with a machine learning-based quality of transmission estimator. So what happens here is when you have created a service going from point A to point B in your core network, this goes through actual fibers. And each of these fibers have their own characteristic, like the fiber, the length of the span, or like, let's say, the length of the fiber, the number of fibers which are there from point A to point B, and the kind of data or kind of the channel which is being carried on this fiber. So the modulation formats, the attenuation, the symbol rate, the channel bandwidth. You have a bunch of parameters which are already available to you. And using this, you need to calculate the signal-to-noise ratio. And the signal-to-noise ratio in for us optical guys is really important, because this really tells you whether or not you are able to achieve the particular data rate which you are guaranteeing your customer. So in order to calculate the signal-to-noise ratio, you need to find the noise. And the noise can be split into linear noise and the nonlinear noise. And the issue is nonlinear noise is really difficult to solve. If you see here, it's like a triple integral, so you cannot always run analytical models and try and find the solution to triple integrals for, I don't know, like for a 80-channel network, for every time you add or remove a channel in your network. So for this, what we did was we calculated the other parts of the signal to noise ratio using the physical model, so just calculate it in a normal way. And we offloaded the cross-channel interference calculations, which is basically all these triple integrals you see here. This was offloaded to the machine learning model, where we basically created a simulation list of previously simulated data, different kind of spans, different kind of fiber lengths, so on and so forth. Once the simulation data was created, we trained a simple machine learning model based on a gradient boost, so like based on XG boost. Tried doing the whole test, validate, train, test, validate, train. Get back a trained model and try and verify this on another simulated devices. So this was our first, let's say the first step or the first foray into using machine learning. And I will show where this is helpful in the further slides. So once we were confident that we can do something with ML, the next step comes as trying to add different things into it. So we go to step number 3, is can we really take data out of network devices in a quick manner, in an efficient manner, store it, process it, and get some informations out of there. So what we did was in the context of iNet Protect, which is also which is a Celtic project. I don't know if you guys know that, but this is also funded by the German government. And here, what we did was with one of our customers, we had access to a very long link, let's say, or like a round trip link from Tallinn to Poznan and back. And what we had was Adva's terminal devices, which is the Teraflex terminal devices. These devices can have anywhere between, I mean, each channel over there, each network channel can do anywhere between 100 and 600 Gbps per second. Sorry, Gbps, depending on how long your distance is. So what we did, we had access to 5 channels in the customer network, in a live network, which is actually carrying live traffic. And our job was to try and monitor or try and extract as much as data as possible for a given amount of time. So how we did that was we were able to access the optical performance monitoring data, which is available through Adva's devices, using SSH and netconf. And what we did was we just polled these devices, and we were just taking the data out and storing it into a time series database in Munich. So this is where our team sits, and we wanted to have it as close to us as possible. And we did this data collection for a long time. Once we had enough data, we were able to, again, develop some machine learning algorithms to check different things, like try and see if there is an anomaly in the network. You're measuring 5 channels. If the power goes up and down, you really see it when you're measuring something. You try and measure the state of polarization. You try and see that if there was something wrong with the fiber, somebody moved the fiber, or if there was a thunderstorm. You see these kind of things if you are monitoring your like these channels 24/7. However, the machine learning algorithms here were not so great. So it was a good idea. We learned a lot in terms of how do you extract the data, but we were still a bit lacking with the machine learning aspects of it. So this is why my friend Carl Wiggum is like this machine learning model which we had. Then now that we had the ML idea and something about telemetry, we moved on to intent-based operations, which meant that can we actually use some relevant use cases? Can we add some use cases into the setup? So one use case which we added again with iNet Protect under the ambit of iNet Protect was that if you have like you have heterogeneous devices in your network, and you really want to use this to uh, use this to mention or monitor the security of your particular area. Now, this security is not only data level security. I mean, it's not only physical layer security, but also the actual security of the premise. So for this, we had three devices. One is Adva's ALM, which works on coherent optical time domain reflectometry, which means that you're sending a signal through the fiber, and the moment somebody moves, somebody cuts the fiber or bends the fiber too much, you see a peak in the curves over there, so you know exactly the location where somebody did something wrong with the fiber. The other thing was we had some Adva's encryption cards and also some QKD devices from ID Quantique. And here we were just measuring a whole different lot of things in order to see that if somebody is messing with the encryption devices, is somebody messing with the QKD devices. I mean, we could basically take data from all these different kind of devices, put it on a cloud server. Now, the trick is with the ALM, you can use it directly to read out the fiber, or you can do a sensing task. So you can connect like passive sensors to the ALM and have different kind of like, let's say, sensors along your fiber. So we had two use cases over here. One was a fiber cut. So if a fiber is cut, then the machine learning algorithm could detect where exactly was the fiber cut in the order of a few centimeters. So it would tell you 59.645 kilometers, something like this. Or we had a door sensor. So we know the locations where you would install a door sensor on your fiber, and it would just monitor whether or not the door is open or closed. Now, this is helpful in scenarios where you have some form of equipments or cabinets out there, and if you could just attach to the fiber door sensor, you would know whether or not the technician who came to repair the fiber or the technician who came to repair the device, did he really close the door or not? So this is what we were going for. And again, put everything into a time series database as we did before, and try and use data analytics to display everything using a Grafana-based web dashboard. And of course, we had demonstrated this also in TNC this year and OFC this year. So if you want more information, this is the paper over there. And finally, coming to SDN, like if we have all these three, can we also do it on an SDN-based network? And this is something which we will be presenting in a conference in 2 weeks from now in Thessaloniki, the IEEE CNSM. And here, what we went for is to have an SDN-based controller and a network orchestrator, and combine it with machine learning as well as a complete streaming telemetry-based automation. So first and foremost, our orchestrator is also a network planner. So this is something very rudimentary, does network planning. If you give it a sort of a network topology, it will do the optical services planning for you. It will give you the list of candidate light paths. And once you have these light paths, you need to know whether or not they work. So this is where we use the ML-based QoT estimator, which I showed you before. And once we knew that, okay, these are the certain light paths which would work, we used an optical domain controller based on open daylight. It's called Transport PCE. And using the RESTconf interface of Transport PCE, we were able to push our services down to the controller. Once the services were pushed down to the controller uses netconf in order to configure each and every device in the network. So for this particular proof of concept, we used Adva's Ensemble simulator, and we used the FSP 3000C devices, which are flexible optical networking devices. And here, each and every device, each and every ROADM device is like a netconf agent, has its own netconf agent with its IP address and the port. So the optical domain controller can, in principle, talk to these guys quite easily. So the moment you give the command that I want to provision a service between node A and node Z, um, transport PCE would go to each and every node and configure it in such a way and reserve the channel and reserve the frequency, central channel frequency and everything, so that you know that, okay, you have a service created. And once the service is created, what we do is we try and monitor these simulated devices for their health to see that everything is okay, everything is all right. And this monitoring service, of course, is based on a time series database. And then we implement the anomaly detection ML model. You remember Carl Wiggum, which I showed you before. So this guy is a bit better than Carl, but we're still getting there. And what it tries to do is try to detect any sort of anomaly in optical receive power, any sort of anomaly in SNR, and give the information back to the orchestrator. So once the orchestrator gets some information back from the network, it tries to reconfigure the service again, and then you have a complete closed loop without any intervention. So this is, again, as I say, it's a proof of concept. It really does only network provisioning right now and re-provisioning and rerouting of services. But at least with this, we can show that you can take things, different things together, put it, and try and come up with an innovative solution. So all this while, I've talked about data, 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 but what I've not talked about is data security. The issue is that you have multiple operators who want to learn from each other, multiple domains, but they cannot share data. You have vendors who want to learn from operators, but operators cannot share data. A way to make life better for everybody is try and share data the way a lot of other guys are doing it, is by using something called as multi-party computation, or by using something like federated learning, where if you as a data owner have some proprietary data, you can use some sort of pre-processing and get your data cleaned inside your particular, let's say, your particular premise. And once this is done, you could use this data to train a particular model. Once this model is trained, you put this model up onto a cloud, and this is where different models are also put from different data owners onto the cloud. And then you have one particular model which learns, like a model of models which learns from this. And with this sort of information, you could do some form of an inference and a query from the network operator and try and see how exactly your devices work or how exactly your devices are configured. And the best part is that all of these can be in separate domains. You're not really sharing data, you're sharing models, so your data is secure. This work is also again done with INET Protect, and it's done by our colleagues, our project partners from Fraunhofer HHI in Berlin, Germany. So the papers I mentioned are over here, and they're pretty interesting to read. All right. So I would like to close. I think I've taken a lot of time over here, but I would like to close my speech saying by what we want to take away from this talk is that disaggregated networks or partially disaggregated networks will definitely drive down deployment costs. It will make things easier in terms of capital expenditure, but integration is always a big deal. And what we want to do is we want to keep the integration costs as low as possible. Some form of privacy preserving ML techniques are out there, and I hope that you get to see it in the coming future really soon. And of course, last but not least, if you try to invest in SDN, in streaming telemetry, in ML analytics, you are going to be the winner at the end of the day, because this is the kind of thing which can really make a difference between you and anybody who's not doing this. So if you are interested in our research, this QR code, I'll leave it out here. We have all our papers out there. And yeah, so that's it. Thank you for your time. And thank you, Netnod, for giving me this opportunity to speak.
Thank you, Sai. We would have time for 1 or 2 quick questions if anyone has anything for Sai. Otherwise, I think we will all be happy to head off to the fresh air of the coffee break. So great presentation. Thank you once again to Sai.